Okay, everyone, welcome to WASAS, the Warm Lecture Room. This is the topic of loss distribution, part 2. Uh, we left with the last time with the estimation, so let's begin with the estimation. So, the first estimation method that we are going to talk about is the method of moment. So, what is it about? This is from the summary of at the end of the chapter in the CT6. The method of moment is blah blah blah. Okay, you could try to read it, but I will show you what it means by example. So let's say the idea is, let's say you have a data. You have data x1, x2, x3, and so on to xn. Okay, and then you assume that this data we have a distribution. Let's say a Pareto. Okay, let's say or gamma. Okay, let's say a gamma. All right. So if it's gamma, what is ex? Ex is alpha divided by gamma, right? And you can also find the sample expectation from those data we have, right? So we just take sigma of x divided by n. So you will have an equation here, and if the distribution have only one parameter, let's say if it is the exponential, you can just use this one to find lambda, right? Quite simple. But if it has two parameters, you may require more than the first moment. You may also require the second moment also, the second non-central moment, which is e of x squared. And e of x squared is of gamma is alpha multiplied alpha minus 1 divided by lambda squared. And the expectation of x squared from our sample can basically obtained by xi is theta square, take summation, and then divided by n, right? So you have two equations with two unknown parameters. Then we can solve for those unknown parameters, right? And this is the idea of method of moment. Okay, so let's see the example. We have the random sample claim with n equal to 20. Okay, n equal to 20, and we believe that this claim will follow the Pareto distribution with parameter lambda and alpha and lambda. So as we say before, the expectation of this claim is the Pareto, right? The Pareto is lambda over alpha minus 1. Is it? I think it's just this one. Let's see. The Pareto. Yeah, lambda divided by alpha minus 1, and the expectation of x squared is 2 lambda square alpha minus 1 alpha minus 2. Okay, so for the first one, the expectation of x from the data we will have is equal to the sigma of xi is observation divided by the number of observations, or from the equation we will have the 1508 divided by 20, and this will give the value of what. Sorry. Okay. And this will give the value of 75.4. Okay. For the second moment, this is equal to the 250, 700 and 212 divided by 20, and this will give 1280.6. Okay, then we just have to solve this equation. So for the first equation, for the first one and the second one, the first one we have to adjust a little bit, just square them. So you will have the lambda square divided by the alpha minus 1 square equal to 75.4 square, which is 5685.16, and this is our new equation 1. And for equation 2, we just divide it by 2, so it will have sigma lambda square divided by lambda minus 1 multiply lambda minus 2, and this will give the value of 6430.3, and this is our new equation 2. Okay, so to solve this one, you just divide the second or first. Which one should be better? Let's see. I will divide the first by the second. So the lambda square will cancel out, and we will have the lambda minus 2 over lambda minus 1 left equal to, we just do algebra a little bit here, so we will have this one equal to the 5685.16 divided by 6430.3, and this gives 0.88412. So we move this one to the other side, and then we move this one to the other side, so we will have 1 over alpha minus 1 equal to 1 minus 0.884412. So alpha equal to this is value of 1 over alpha minus 1, then to the power of negative 1, you will have alpha minus 1, and then you plus 1 to get alpha. Alpha will equal to 9.629.6. Okay, and just substitute this one back into the first equation or the second as you wish. So let's say I plug this one into the first equation, so my lambda will be equal to 75.4 multiplied by the lambda minus 1, so it this one multiplied by 75.4, which is 650.6071. that is what we have from the solution, so we good. Okay, so this is the example of how to use the method of moment, and then we move to the method of percentile. Thing goes similar, so we just derive what it should be the median in theory, and then we compare to the median from the observation. So the example here we have a bird distribution. Bird distribution have 3 parameters, and we are told that the 2 parameters are given. So we just have to estimate actually just 1 parameter. So we will find first what is the distribution function of bird distribution, and what we have is 1 minus lambda, this one. Okay, so it is 1 minus lambda 200 to 200 plus x to gamma here is 1.2, and over all to the power of alpha. Okay, so this is the distribution function, and by setting this to 0.5, this x will be median. So what we have to solve is we will have this one equal to 0.5, and this x we are told, right, the one that we will plug in, we are told that the median from our sample data is 420, so we can just plug 420 here. Okay, we plug 420 here, so our lambda will be log of 0.5 divided by log of 200 divided by 200 plus 420 to the power of 1.2, just that. And for estimating parameter we need head, right, because this is from the estimation. Do we need it? I'm not sure, just see in the solution. I'm not so profession with the hat thing. So let's see this one, what we will have here. Okay, so this one is log of 0.5 divided by log of 200 divided by 200 plus 420 to the power of 1.2, and this gives 0.3328, which is what we have for the solution. Okay, so we are good. And also, if you remember, we already derived the formula for the median of bird distribution here, right? So we can also just plug 420 here, 200 here, 1.2 here, and then solve for alpha here. That is the same thing. Okay, so there is something that I want to mention about the method of percentile. So which is the textbook tell that the adequacy of the method of percentile is quite low, which if you want to use the method of percentile, you will need like a thousand of observation to have a accurate method of percentile. You have to have like over 1,000 of observation. And also there is another thing that I want to mention. So what about we want to estimate 2 parameter or 3 parameter? So for 1 parameter you take the median or the second quartile, right? For 2 parameter we may have the first quartile and the third quartile. For 3 parameter, just 3 of them. Fair enough? Yeah, that's it. Okay, so that's all for method of percentile, and then we move to the maximum likelihood. The maximum likelihood, because we have faced with this method like many times before, so I choose the question to be a little bit hard, because I think everyone have already familiar with this method. So to wrap up, the maximum likelihood estimator, just first step, you write down the likelihood function for the available data. The likelihood function is just take the product of all PDF, and then to simplify easily, you may take natural log, then you maximize, and then you solve the equation that you obtain from the differentiation in the step 3, and after that in step 5 you just verify that that point is the maximum point. That's all. Okay, so we will try to do this one. This one is the random variable y on the range 1 to the infinity have a log gamma distribution. So it means that log of y has gamma distribution with parameter alpha lambda. So the first one here that we are gonna do is show that the PDF of y is this one. So y follow log gamma alpha lambda. Okay, and then x equal to log of y will have gamma alpha lambda. Okay, so probability of the y less than x, the probability that y is less than x is equal to probability of e to the power of x less than x, right? And then we will have probability of x less than natural log of x. So we just have to plug it in the distribution function of x, but x follow gamma distribution, which means we don't have a distribution function for it, right? So we just leave it in the form like this, f of x. So this one is mean the distribution function of x less than log x. Okay, then we take the differentiate of this function. We should get the PDF of y, f y x. We differentiate this one respect to y. Okay, so to make things easier, just to make things easier, there is nothing more than that. We will change this x to y, so the thing we can see clearly, and also it will be the same form as we will see in the solution, so it will be easier to follow. Okay, we differentiate respect to y, so fx here will be fx of log y. Then we have to differentiate inside because of chain rule, so differentiate log y respect to y is 1 over y, and f of x of log y is lambda to the alpha gamma of alpha log y to the power of alpha minus 1 e to the power of negative log y multiply lambda. And then 1 over y, right? So just do a little of algebra here. We will have lambda to the power of alpha gamma of alpha log of y to the power of alpha minus 1. This one here is e to the power of log, right? So it cancel out. It will leave you with y to the power of negative alpha, and we have 1 over y, so just one more negative, and this is what we expect to have here, the same. Now we move to the part 2. We try to do the estimation by maximum likelihood method, right? So the log likelihood function of alpha and lambda here is just log of product for all data of f y y, right? And f y y is the one that we just obtained in the first part. So what will we have? To easily understand this one, I have to explain like this. You have to take the product of this one multiple times, like, right? And then you take log, so you have log applied to it all, and then it will be the log of product. It will be the summation of log. So in other words, this equal to of log f y, like this, right? So let's see. So we will have alpha sigma of log lambda minus sigma of log gamma of alpha, then plus alpha minus 1 of summation log of y, okay, then plus or minus, because we will pull we distribute the minus out, factor out. So inside we have just alpha plus 1, lambda plus 1, and log y, and also sigma. And you have to keep in mind that this sigma will apply on the y value, because the y value will have index I to it. The other is just constant. So this is our log likelihood function. Now we just take a differentiate respect to alpha first. Respect to alpha, you will have lambda. Let's do lambda first. When differentiate respect to lambda, what will we have is alpha log lambda will be 1 over lambda, and the summation of the constant will be just another n, right? This term doesn't involve lambda, so do this term, but this term have, so you have a negative of sigma log y and to 0. So what you have here is lambda is equal to n alpha divided by sigma log y. Okay, now let's do the differentiate respective to the alpha. To the alpha, you will have n log lambda, right? Because this alpha cancel out. This is summation of a constant, so it will become n log lambda. This term also have alpha, so you will have, but this summation doesn't have y term in it, so it's just the summation of constant. We will have just n, and then we differentiate log of gamma of alpha. So we have 1 over gamma of alpha. Then we do chain rule, so we have to differentiate the gamma of alpha too. We have this one, right? The next term that involves the alpha, is this term, and this term is a plus sigma I from 1 to n of log of y, right? And we know that our lambda, this one, will have the form of this one, because we have to solve this one and this one equal to 0 to find the maximum point, right? So we just plug this one here. You will have n log n alpha divided by sigma log yi first minus n gamma prime of alpha divided by gamma of alpha plus sigma of log y i. That all to 0. And this is what we try to prove. Alright, so let's go. Let's move to the next one. Next one is about the appropriate method for each distribution. The first one, the exponential, it's easy to do anything. The MLE, the method of moment, the method of percentile, all of them can be done easily, right? Because the distribution function is easy to derive. the PDF is easy to derive, so we can have the likelihood function easily. The moment is quite simple form, and so do the distribution function given in the nice form. So we can just apply all of them if we want to. The gamma is say here that it's not easy to apply the MLE for the gamma, but we can just try to use a different parameterization by use the parameter of alpha and mu instead, like what we do in the TLM. Okay, then the normal. Then we move to the normal. The normal, we just use the moment or the MLE. It's just the same thing. The method of percentile is not easy to do because we have no code form of distribution function, but we have a table. Who cares? The Pareto, we can easily use the method of moment as we did in the question 3.12, the one here, this one. So yeah, about generalized Pareto, the CDF doesn't exist in the code form. The method of percentile will therefore not available. The maximum likelihood can be used, but it's suitable for computer software because it just doesn't easy. But however, the method of moment can be done because we know the expectation. The form is that doesn't that hard, but to do all three parameter, it should be hard. So if we know one or two and we try to find the other, it might be possible. The log normal, we just take log first. So you have the normal, and later you have the normal. You can just apply the moment or the MLE. Doesn't matter. Same thing. The variable, you can do method of percentile since the CDF exists in the closed form, and also do the burr. Same thing. Okay, and this one is quite interesting to note. If the gamma are known, the variable and burr can be solved easily. Why? Because if we have a look here, the way we obtain the burr and variable is we transform exponential and Pareto by the Pareto and exponential by x to the power of 1 over gamma. So if we have burr and variable and we just transform by x to the power of gamma, it easily come back to Pareto and exponential, which are easy for estimation, right? Pareto is here, exponential is here, not that hard. So if we have x follow variable, y follow burr, the transformation z equal to y to the power of gamma will transform the variable into Pareto, and z equal to x to the power of gamma will transform the burr into exponential. No. Swap. Burr will become Pareto, variable will become exponential, right? Variable exponential, variable become exponential. Okay, Okay, so next one, the goodness of fit test. This test is check whether the model fit the data good enough or not. So the way we do is that, let's say we have the loss in each interval summarized at this table. Okay, at this table. So we fit it with the exponential distribution, and we have a hypothesis this is when it comes from exponential distribution or it doesn't come from the exponential distribution. And from the earlier example in the textbook, we already estimate the value of parameter already, which is 1/2200. I did not include it here, but just follow it. Okay, so we already estimate this one, so we can try if it fit by this exponential. The loss between 2000 and 3000 will can be obtained by just by this integration, and the probability of loss falling in this interval is 15%, right? So in a total of the 1000 claim, we would expect 147.2 claim in this band. The same way candidate with the or other band. So we will have this. We will have this loss for perfectly fit exponential with this parameter. Then what we do, we take the observed minus the theoretical square over the theoretical. Then we summation it. We take summation, and this should give the chi-square distribution of degree of freedom 6 minus 1, because we have a total of 1000 that decrease degree of freedom by 1, and also the one more because we already estimate one parameter. Make sense? So we have a chi-square of T31, which is greater than the upper tail of 99.5% at equal to 14.86. So we reject the null hypothesis and summarize that it doesn't come from exponential distribution. So actually we just calculate this one is enough, because just this one is exceed this number already. Or if it is exponential, we would expect to see the value decrease at its goal, but this one is an increasing. So we can roughly tell here too that this one shouldn't follow the exponential distribution. Okay, so this is what the goodness of fit is about. Okay, move on the last topic, the mixture distribution or the marginal distribution. This one I would say is kind of a little bit like a Bayesian that we have studied. Just that the mixture distribution doesn't want to know what category that the parameter will be in, right? Because if we talk about the Bayesian, we talk about f of some parameter, some unknown parameter given x, right? Value of this parameter equal to 5 given the data, the series of data is equal to, but this one is opposite. We just talk about the marginal of x which means we take all of possible outcome and sum it together, just like that. So okay, let's see the example, and here is a formula I already provide here. So for this one is not about the question, you can cancel it out. Okay, the question start here. Let's assume loss has follow the gamma, k, and lambda, and lambda is unknown. It's very in not the lambda is not constant. It varies to each side of claim, right? And we have known that this lambda gonna follow the gamma of alpha delta. Okay, so we would say that the probability of loss x will occur from the loss x of alpha of one value of lambda, then we multiply by the probability that the lambda will happen in the first place. So we will sum it all up and you will have the probability of x, right? So for example, probability of loss and 500 to occur, it might occur by loss of 500 when lambda equal to, let's say, 2, and then you have to multiply by the probability that lambda equal to 2 at the first place, and then maybe the probability that the loss of 500 can occur, it maybe can occur by the lambda equal to 3, and then you have to multiply by the probability that lambda will equal to 3 in the first place, and so on. So that is the mixture distribution about. It is a marginal distribution. So we sum all lambda here to obtain the mixture distribution, the marginal. The probability of x given lambda is the gamma k lambda. So we put gamma k lambda here, right? And also the probability of lambda will happen in the first place is gamma alpha delta. So we put gamma alpha delta here, and we just try to manipulate a little bit. So finally we will have this one as a marginal distribution, because after we rearrange a little bit, this one is gamma distribution and it come to 1. So finally we will have this distribution, and unfortunately this one is Pareto alpha lambda k. So this give another interpretation of the generalized Pareto distribution. Generalized Pareto distribution is a mixture of the gamma where the lambda is unknown and that lambda is follow another gamma, right? Makes sense? Yeah, that is what the idea of mixture distribution is about. So let's try to do our last question. This question want to model the number of claims, so whole number. Okay, so the probability that the claim number occur follow the Poisson with parameter theta, but theta is not fixed. Theta assumed to be gamma of alpha lambda, and therefore we want the mixture distribution for number of claim. What will we do here? So we say our x is the number of claim, so probability that our x is equal to x will be the probability of x will occur from the theta, right? The Poisson of theta, then probability that x occur. But we also have to calculate the probability that this theta will occur at the first place. So it will look like this. As a marginal of x, it will look like this. Okay, so we just do some calculus here. This f of theta is gamma alpha delta, so delta to the power of alpha gamma of alpha theta to the power of alpha minus 1 e to the power of negative theta, delta theta. Yeah, this is the prior, and then the log, the Poisson. The Poisson of theta is e to the power of negative theta, right? Theta, right? Theta to the power of x divided by x factorial d theta. Okay, so we just rearrange a little bit. We put things together, so theta power of x plus alpha minus 1, then e to the power of negative delta plus 1 theta. Why we write this one? Why do we always write this term first? Is because this is the main two terms that need to identify the gamma. This one will be lambda in the gamma distribution, and this one will be alpha minus 1 in the gamma distribution. So this one we have our gamma be equal to x plus gamma and lambda equal to delta plus 1. So we need here the delta, the lambda to the power of gamma and alpha of gamma, like this, right? So let's see what adjustment that we did. First, this one we need to pull it out. This is the differentiation of theta. X had nothing to do with it. We can pull it out. So 1 over x factorial can pull out. Then we had adjust this one, so we make it to be the same by just divide it out and multiply the original in. Okay, and the last one is this one. We take gamma of x plus alpha, we divided it here, so we multiply it in here, and then we put the original in, right? And this one will come to 1. Why? Because this one is gamma of x plus alpha and delta plus 1, right? And thing here is it can be derived into x plus alpha. The x fact is basically just gamma of x plus 1, right? And then gamma of alpha. Then we have the delta to the power of gamma divided by the delta plus 1 to the power of x plus gamma. We can just arrange a little bit here to be delta divided by delta plus 1 and all to the power of alpha, and then the rest we put it aside, 1 over delta plus 1 to the power of x. Multiplying this will give the same result as this one. But what we're trying to do here is try to make it in the form. So recall that what we mentioned earlier, x is whole number because we talked about it, the number of claim, right? And this one is basically the one that I put it here. It's a negative binomial of type 2. It's the same thing, right? So the posterior of boson and gamma will have negative binomial of type 2 with parameter alpha, and p is delta over delta plus 1. That's all for this chapter. Hope you enjoy and see you on the next lecture. Goodbye.